Happy to be here today to talk a little bit more about what we're doing at Velo3D and how we think we may be able to help engineers as they design really challenging systems. So as an engineer, your job really is to come up with innovative solutions to challenging technical problems. And especially on the design side, there tends to be kind of this drive to design the optimal part, whether that's through just pure design software or utilizing computer-aided engineering and CFD and FEA to really optimize every part and every component in a system in order to get the maximum performance out of the system that you really can. And I think as an engineer, one of the things that people are really used to is compromising on those designs. So even if you have an idea of how to design something to really fully leverage the performance of a system, you really tend to need to make some amount of compromise. And generally, this is due to manufacturability more than anything. And that's something that we've seen at Velo3D and that we really want to help to address so that we can help our customers make the most innovative, most high-performance systems that they can. And I think the focus today is specifically on turbomachinery, because that's where we've seen a lot of possibility and actually a lot of realization of this potential. So in turbomachinery, generally you have complicated fluid paths and surfaces that are optimized aerodynamically, and those tend to be difficult things to manufacture. As a company, we find that we do best, our technology does best with things that fluids flow through or that transfer heat. And turbomachinery absolutely falls into that category and is maybe one of the best places to use additive manufacturing, and metal additive manufacturing in particular. And we really, as a company, tend to focus on helping our customers achieve these optimal designs. And we want to talk about it in terms of the customer success, because that's really, I think, what's most important and what speaks to other potential customers and people who are looking to use metal additive is kind of seeing the success that others are having with the technology. So one of the companies that we've worked with and that you may have seen some of our press about in the past few weeks is Sierra Turbines. They're a company that is manufacturing microturbines for UAV and distributed power generation applications. And Roger Smith, the CEO of Sierra Turbines, has been looking for kind of a manufacturing solution to help him capitalize on some of his designs, some of his optimal designs. And we worked very closely with him. And I think Roger was extremely happy with the results that we were able to deliver to him in terms of his optimal design. And actually, this is the part that we were making with Sierra Turbines. So what Velo3D does is give our customers our support-free technology, which allows them to print parts that really were not possible to print before. And metal additive manufacturing has, long had a promise of being able to print very complex designs and to do so in ways that you really couldn't consider before. But Velo3D really is one of the first to truly deliver on that complexity without cost and design freedom promise. And so in the case of this combustor liner that Roger and the Sierra Turbines team were designing, they were looking for a manufacturing solution for this part for some time. And there's a lot of challenges with this part that SupportFree helps to address. Here we're highlighting some of the specific geometries that we take into account in our system and provide very specific printing recipes you can think of in order to have a solution. And when you combine all these things together, it really allows the design engineer to fully optimize the part for any given application, which is really our goal as a company. So in some of the turbomachinery applications, I think one of the questions that we often get asked is around the quality of the parts we make, kind of the production quality of the parts that we make. And I think there's still a lot of education that needs to be done in general about what laser powder bed fusion is capable of and even whether or not the material is, is real, fully dense, usable metal. And laser powder bed fusion in general is very capable of making, high density, nearly 100% dense metal that achieves the mechanical properties that you're looking for. And Velo3D has taken kind of that core capability and pushed it to a much wider range of geometries with the support-free capabilities that I mentioned in the previous slide. And if you're summarizing that, really it's about printing extremely high quality material, even at very thin, high aspect ratios or at very low angles. And that's really what we're kind of focused on delivering to the customers is the geometric capability at the consistent quality that you need, especially in really demanding turbomachinery applications. And so some of the things that we want to focus on and kind of highlight here are the surface finish, porosity, and the mechanical properties of the material to demonstrate how usable it really is in these applications. So when I mentioned that we tend to focus on parts that fluids flow through, I think one of the first questions that we get is around surface roughness. And if you have experience with metal additive manufacturing, whether that's laser powder bed or electron beam, you may have had experiences where the surface finish is not what you're used to getting from a machined part. And I think that still holds true here. It's not going to be a 16 micro-inch finish directly out of the machine, but Velo3D is definitely pushing the surface finish to a much better level than what you see from some of our competitors. And more importantly, doing it over a wider range of angles. So when we say angle here, we're looking at a downward facing surface for everything below 90 degrees, and then 90 degrees is a vertical wall and upward facing surfaces above 90 degrees. And this is a printed gauge block that shows some of the low angle performance of the support-free process. And when you're looking at the surface finish as a function of angle, you can see that as you get to lower angles, lower overhangs, you tend to see the surface finish not be quite as good as it is at a vertical surface or a vertical wall, but still very useful in the vast majority of turbomachinery and even heat exchanger applications that we tend to work in. Another question that we often get asked is around porosity. I think there's a lot of historical data that shows that printed parts tend to have porosity. And especially in kind of fatigue-driven applications, that porosity can be really problematic. A lot of times what you see is what we call a lack of fusion porosity. And that's a porosity that kind of looks like an internal crack, where you essentially have two parts of the metal not fusing to each other well. And it's a problem in fatigue applications because it actually is a crack propagation site. So that is generally an area of concern. In our printed parts, we don't see the lack of fusion defects that you would in a lot of our other competitors' systems, but you do still see some amount of porosity. So we want to be kind of upfront about that, especially as you get to the near surface. You have what are keyhole spherical bubble porosity. And that's important to point out because it's there and it's something that you should account for. That being said, we've done quite a bit of extensive testing on not only the static mechanical properties, but also the fatigue properties of as printed and machined parts to demonstrate that this level of porosity and this particular morphology of porosity doesn't have bad effects on the end mechanical properties. So here you can see kind of the near surface micrographs for both as printed and hipped material as a function of angle. So this is actually section and cut pieces that have gone through hipping here on the right and then straight out of the printer on the left. So we talk about support-free as a capability, and really when we talk about support-free, what we mean is being able to print critical geometries without requiring support material. This is a printed part that we did with Stratasys Direct Manufacturing for Hanwha power systems as part of a supercritical CO2 application. And there are a couple of white papers, both from Stratasys Direct and from Velo3D, that we have on our website that go into a little bit more detail about the story behind this part. But for context, this is about a 10-inch diameter shrouded impeller that was printed in Inconel 718. And you can see this is actually how the part came out of the printer. So this is with a support wall around the OD of the shrouded impeller, and then some small amount of supports on the bottom of the part. I wanted to provide this picture because it's important to consider this in the context of the actual part, which you can see here. So this is the fully machined and polished part that Hanwha was going to be using to test in their supercritical CO2 system. And I think the important thing here is that after post-processing, the part is really a truly useful high-performance turbomachinery part. Depending on what you're trying to do, the heat treatments can differ. We've seen differences between even industries, right? So aerospace grade heat treatments are sometimes not necessarily what you want to do if you're working in the energy sector and you have maybe API certifications that you need to meet or NACE certifications. So that's an important thing to be considered whenever you're going to have a final part. But essentially it's a heat treatment, cutting from the build plate, and then some amount of machining and surface treatment to get to your final surface finish. And the surface treatment is an important aspect of this because, as I showed in the surface roughness plot, I think if you're an aero guy or you are an engineer dealing with aero guys, one of the things that you'll run into is that the requests for surface roughness are generally pretty strict. You know, getting additive parts to those surface roughnesses in the past has been a challenge, but the Velo technology actually allows for the manufacturer to get to those surface roughnesses with less effort. And this is a really cool example that we worked on with Barber-Nichols of a shrouded inducer. And I personally like this application because a shrouded inducer is not something that you run across very often. In terms of manufacturability, a shrouded inducer would be fairly painful to make with traditional manufacturing. But with Velo's support-free technology, this is something that we printed without any internal supports, and kind of as you see it here on the bottom right. This part, just for context, is about a 4-inch diameter on the shroud. So it's a reasonably sized inducer. And they were able to achieve with an extrude hone process a surface finish of 14 microinch max on this part with only 10 thou of material removal. And that's important to note because a lot of times when you're going through post-processing of printed parts, you tend to have to remove a lot of material to get to the final surface finish. And that has a lot of adverse effects in terms of the dimensionality of the part. If you're having to print extra stock to then account for that material removal. But with the Velo process, you can get to that final surface finish without removing too much material. So it's much easier to kind of maintain dimensionality while hitting the right surface finish. The other question that we get asked and that I kind of alluded to earlier was around mechanical properties. Is it real metal? And the answer is absolutely. This is actually very good metal in terms of the mechanical properties. So in general, we tend to be better than cast material across the range of alloys that we offer, and approaching that of wrought components. So this is a comparison of the mechanical properties to the ASTM F3055 spec, showing that we're definitely above the spec limits as far as the mechanical properties go, both for the as printed components and for the finished machine components. And we like to point that out because often if you're looking at like a casting, what you're doing when you're looking at the mechanical properties is taking a casting and machining a specimen, a mechanical sample out of that. So it's almost always machined, whereas in the actual application, not every surface is going to be machined. So it's important to test and to validate that the as printed surface is giving you the mechanicals you need as well. And that's especially important in fatigue. So the fatigue properties are very sensitive to the surface finish and to kind of the morphology of the surface finish more than anything. And so this is a couple of plots that just show the unmachined, the as printed, and the actual finished machined fatigue values for our Inconel 718 material. across a range of stresses, but then also at 2 different print angles. And the reason we think this is important is if you're going to have a part that ends up with some as printed surfaces, you need to have confidence in the fatigue characteristics of that part. So when we print the blue dots, they're 45 degrees unfinished, tested to fatigue limit. And they were comparing those to a 90-degree surface tested to failure as well. And you can see that in general, even with a slightly rougher surface, the morphology of our part means that in a fatigue application, they still perform very well. So the support-free process is kind of a new capability that allows engineers to truly leverage their optimal design and to make the optimal design with confidence. For us, this really comes down to a few main bullets. We're able to print very low angles without supports, critical for many different aspects of turbomachinery, whether it's rotating components or static components and gas turbines, turbo pumps, all different types of applications. And then to have the appropriate materials for these applications. And what we've listed here are our available materials. And you can see that it's very focused on traditional kind of propulsion and turbomachinery alloys. We're also working on several other new alloys, and we're happy to take suggestions as to what might be valuable to our customers or prospective customers. And then the parameter sets are available for our different machine configurations. So our standard machine is a 315 millimeter diameter, or about a 12.5-inch diameter, with a 400 millimeter build height, which is 16-inch build height. We're also now offering that in a 1 meter configuration. So it's the same diameter, but with a 40-inch or 1 meter tall build volume. May not be as applicable to some of the turbomachinery applications, but we definitely have run into some pretty interesting use cases for it. So being able to print the geometries that you need to print and having some idea of what the base mechanical properties is definitely an important step for a designer to have confidence in the ability to use this manufacturing technology for their products. But there's still one unanswered question that we run across quite a bit. And we're really, coming from more of a kind of a rocket propulsion background, rocket turbomachinery and combustion chambers and injectors. And so we deal with NASA quite a bit. And NASA actually has some of the best, most well-written standards when it comes to qualification and certification of parts and processes from laser powder bed fusion. And one of the things they point out that I think is really important to consider is that while laser powder bed systems in general are capable of making high quality parts, you don't necessarily know if a specific part that you pull off of the machine is good or not. So while having like a good average value is important, having confidence in an individual part is critical. And that's something that Velo is also focused on quite a bit. As I mentioned before, the mechanical properties are generally equivalent to cast, or better than cast, almost equivalent to wrought. You get great density and great geometric accuracy from the parts. Here we quote a 0.2% dimensional accuracy. In general, we're tending to do better than that, although I definitely don't want to overpromise on that. So we tend to be able to print the parts per the requirements of the specific application, and then to give validation on an individual part basis. So we have developed a software called Assure, which is our quality assurance and control software that allows for the tracking of the quality of a part throughout the entire print process. We're able to validate that the systems are in spec as you start printing, that the build is actually performed nominally, and that the customer at the end of the day has traceability, which is, I think, one of the most important things for these parts. We talk a lot about design allowables and confidence intervals, and really our goal here is to have a really well-established confidence interval for the quality of the part that you get off the system. So you know that the part falls within your confidence interval and that it's a good usable part for the end application. As I said, Assure is tracking all of the key parameters, the key process parameters throughout the entire build. And this information is available at the click of a button to the users and operators. And it's also stored, so you have historical context as far as the build performance and kind of part traceability. And some of these are kind of interesting. I think if you look at the chart that we have up here, the oxygen level, I think, is a relatively clear metric to be tracking, and something that a lot of our competitors are tracking as well. Humidity is a very important metric. The powder that we use in these systems tends to absorb moisture onto the surface, and then as you're lasing it, you can ionize the water and end up with oxygen or hydrogen. So you need to be able to track that and control that very well. And then the top one is actually, I think, one of the more important ones, and one of the more interesting for our system, which is the peak height. And when we say peak height, what we mean is that we are actually scanning the powder bed every layer with a structured light scanning system to measure the peak height, the topography, if you will, of the powder bed. And this gives us really, really important data as to the behavior of the parts and the behavior of the system. Because if you think about it, we have a welding process. And in a welding process, what you need to know is the amount of energy applied per unit area and unit time to a given amount of material that you're trying to melt. And having optical metrology is one thing, but being able to know about the material that you're trying to melt and making sure that your powder bed is consistent and of high quality is also critically important. And I think that's something that as an industry, you'll start to see more and more that we're really trying to lead the way on, is having that complete metrology set. And one of my favorite parts of the system and of the quality assurance is really what you see on the left here. So this is a tool health checklist that shows the calibration of the system. And this is included with our build reports for parts before and after every build. So in the documentation for a given print, you actually know the calibration status of the machine. And that's something that's absolutely important and key to consistently make good parts and to have confidence in the parts. If the system starts out of spec, your probability of making high quality, consistent parts is not what it should be. And of course, the important thing here is to make it traceable, right? And so being able to document all of this and have essentially a traveler that can go with your part and go to the end user, to the customer, to show them what happened and what they should expect from the part is critical. So as a system, we're really taking this printed part and the digital information that's contained from that print and giving it to the user in kind of an actionable format in our build report. So just as a matter of closing, I think one of the things we really want to highlight is some of the successes that our customers have had, and to show really in an application what you might be able to accomplish. So we mentioned the Sierra turbines part at the beginning of the presentation, and one of the reasons that I think this is such an interesting case study is if you see this part on the far left here, this is actually what the part would require in terms of support from a traditional laser powder bed system. So it's pretty easy to see all these red stripes, which are supports, would make this a completely untenable part to print. And if there's no manufacturing solution for this optimal design, then it just remains an idea. And our goal is really to help capitalize on the ideas to deliver that truly optimal part and make the end system higher performance. So here you can see some of the figures of merit that we're looking at for this particular application. For the Hanwha Power Systems impeller that we're printing with Stratasys Direct Manufacturing, this is again a comparison of the support material required for printing this on a standard laser powder bed system versus what was required on the Velo system. And actually, you can see some of these blue supports in here. That is from about a year ago, and our capabilities have evolved so that you don't even need those parts. The value in this part was really around speed of development. So having kind of a short development cycle and needing to deliver a part that you can actually get into a test rig and run in kind of functional testing was the critical aspect here. So being able to print quickly, to iterate quickly, and to do it more cost effectively really gave Hanwha the the advantage and the capabilities they needed for this part. And then this is another really interesting part. This is again from a microturbine application. This is the diffuser for the compressor of this microturbine from KW Micropower. This is a titanium diffuser where each one of these passages here on the inner diameter is ducted out axially through the bottom of this part. And this is a part that, that the customer actually was asking our competitors to print, but they were unable to do it and referred him to Velo3D as a potential solution provider. So we printed it the first time. We gave them a pretty tremendous reduction in the weight of this part, which is important for the overall engine weight goal, and demonstrated really good performance with this as well. And one last final topic here is around a little bit of the markets that we're targeting. So we've talked a lot about the new product development and kind of allowing the innovation. There's also an aspect of turbomachinery and turbomachinery components that I just want to touch on briefly, which is about maintenance and repair. And one of the things that we've seen is that there's definitely a market for parts that are very hard to source in the maintenance and repair world. And this is another area where we tend to help quite a bit. I think Honeywell is a really good example of a company that not only deals with new products, but also supports a lot of legacy products. And being able to print parts that you couldn't print on other metal printers in the MRO world is also an extremely valuable proposition. So those are kind of the two worlds where we play in terms of parts. And I just wanted to make sure that we weren't only talking about new parts, although sometimes that can be the more exciting world. As a company, our goal is not to sell you a machine. And I think that's an important thing to mention. We are a technology company, but our goal really is to help you make the most innovative solution to your technical problem. And what that means in a lot of cases is finding a contract manufacturer who can deliver you a turnkey part that meets your requirements. So we work very closely with our contract manufacturing partner network, who are mentioned here, in order to make sure that their customers are getting the most successful part that they can. So if there's a part that you're looking at, we're happy to do initial kind of consultations and help show how our technology can benefit that part. And then we have a network of partners who are certified and qualified to deliver that end-use part that you're looking for. Appreciate your time, and hopefully we can work on making some awesome parts together.